Welcome. My name is Christopher Seidel. I look after MDK and CMSIS in ARM. In today's webinar, I show you how CMSIS helps to connect your application to the cloud quickly. You will learn how standardized drivers that are available for a couple of Wi-Fi shields help you to hook up your IoT endnode to your favorite cloud provider in less time. In a hands-on, I show you how to connect with an NXP LPC55S69 development board and a Wi-Fi shield to an Mqtt broker. I also touch on checking your Wi-Fi connection using an out-of-the-box validation suite. CMSIS is a vendor-independent hardware abstraction layer for microcontrollers that are based on ARM Cortex processors. It provides simple software interfaces to the processor and communication peripherals. This simplifies software reuse and reduces the time to market for new devices. Other components include specialized libraries for digital signal processing or machine learning. It also provides an API for real-time operating systems and a mechanism to deliver software components. CMSIS helps to combine software components from multiple middleware vendors. Ready-to-run middleware such as USB or a networking stack require drivers for the underlying devices to be present. To ease the life of the developer, CMSIS-Drivers standardize the access to the hardware and help to avoid cumbersome and time-consuming driver porting. Many microcontroller devices already offer these CMSIS-Drivers and thus help to get to market faster. CMSIS-Drivers provide access to the unified feature set of a certain peripheral. Offering a consistent API for all devices reduces the overall learning effort. CMSIS-Drivers are RTOS agnostic. You do not have to worry about the actual real-time operating system at the beginning of your development project. Also, it makes it easy to change the underlying RTOS at project runtime. Lots of example projects and code templates help you to get started quickly. The CMSIS-Driver API describes interfaces for middleware stacks and user applications. These driver interfaces connect the microcontroller peripherals with middleware such as communication stacks, file systems, or graphic user interfaces. How does this work? In general, middleware or the application software can access different CMSIS drivers to connect to the targeted hardware. For example, a file system component might want to use a USB stick to store data. Then it uses the CMSIS driver USB. If it uses an SD card instead, it might use the CMSIS driver for SPI or MCI, depending on the actual hardware connection. Using the driver validation test suite, you can ensure that your device is configured correctly, and all drivers are set up as required. The validation test suite is available for all CMSIS drivers. The latest extension to the CMSIS driver API is for Wi-Fi. The current available driver implementations either use UART or SPI to communicate with the device or module. A Wi-Fi driver usually provides different access levels. The management interface gives access to the control functions of the module. You can enable or disable Wi-Fi, set power control options, or connect and disconnect to an access point. Most of the time, the module runs a TCP/IP stack by itself that handles the whole data communication for the application. In this case, only the raw data needs to be sent to the module using a simple socket interface. All Ethernet protocol-specific handling will be done by the module. Some modules offer a bypass mode. This allows to run the full TCP/IP stacks on your microcontroller for communicating with the network. In this case, the module only transfers the Ethernet frames via its Wi-Fi hardware. Let's take a quick look at the CMSIS documentation. It is available on GitHub. On the CMSIS-Driver tab, check out the Wi-Fi interface in the reference section. It gives you all the details and includes example code to help you to get started. In this example, you learn how to listen for a socket and that you must bind the socket first. You might ask, why is this important? Can't I just use my own custom driver that is provided by my silicon vendor, together with some code that I get on the internet? The great benefit of the CMSIS-Driver approach is that you can easily create variants of your application or switch to a different target while the project is running. In the past, we have created connectors that allow to use any of the major cloud providers that are out there. These connectors are agnostic of the underlying hardware and only use standardized interfaces. They use a so-called IoT socket component and rely on the industry standard Mbed TLS component from ARM for security. Using this approach, it does not matter to the developer of the application code if his device will connect via Wi-Fi or wired Ethernet to the cloud. He can also decide if he wants to go for a professional middleware solution or take an open source approach. You can learn more about this communication foundation on www.kyle.com/IoT. I show you all this working together in a real-life project. As said in the beginning, I am using an LPC Expresso development board with a Wi-Fi shield from WIZnet. This is a simplified picture of my software stack. My application runs on top of our Kyle RTX5 real-time operating system and uses various drivers from NXP for board support and the UART. It also uses the CmSIS-Driver Wi-Fi for the underlying wireless module, the generic socket component, as well as Mbed TLS and a simple IoT client for Mqtt. My Mqtt broker runs on a fixed hardware platform in my office that emulates cloud access to any cloud provider. Before I verify my application software, I run the validation suite on my setup to make sure that I have used the right hardware and software and can connect to Wi-Fi. Otherwise, I might encounter problems later that have nothing to do with the actual application, but simple configuration errors. Setting up complex SoCs, such as the LPC55S69, requires additional tools and can quickly lead to a non-working project. The validation suite verifies the API interface interaction using the driver capabilities, as well as valid and invalid parameters. It initiates data communication with various transfer sizes and parameters, such as the baud rate. I use the following setup. I connect my target hardware to a wireless LAN router. Using Ethernet, I connect another development board to the router that is running a socket server. Using this server, I can run all the required checks. The application software for this socket server is freely available in the validation suite. Here's the driver validation project. Let's take a look at the software components. So we have the usual software components for device and board support, so the device startup component, for example, and SDK drivers. The board support package, the template that is coming out of MCU Expresso. I'm using CmSIS RTOS2 Kyle RTX5 as the real-time operating system in this case. And of course, we use the CMSIS-Drivers, the USART for communication with the shield, and the Wi-Fi driver for the WiFi 360, which we actually then now test. From the CMSIS-Driver validation group, of course, I'm using the Wi-Fi driver itself, so the tests for the Wi-Fi driver, and I also need the framework for that. Finally, I use the compiler component, the event recorder, and I also use event recorder for standard out messages, so basically for printf. I click OK and open the main file. In the main file, not much happens. We first initialize the device and the board. We initialize the kernel and create a new thread, which is the CMSIS-Driver validation thread. And as this is coming from a library, I can hit F1 on it and I get to the documentation. So this is a feature of Microvision. And I see down here the program flow outline, so initialization of the test report and then testing every group and the test cases that are defined for the group. And finally, the debug session ends. The CMSIS-DV function itself is in the driver validation in the dv framework.c file, and it has the program flow also as a Doxygen documentation element here, and yeah, we see what this function does. In the CMSIS-dv.c file, we see all the test cases for the driver validation of the Wi-Fi, so all the tests that we run through. And we had previously a look at the socket listen function. So here's the actual test of the Wi-Fi socket listen function that's in the dv_wifi.c file. This, for example, creates a worker thread. We will see later when we debug. And finally, of course, we need to configure this somewhere. So in the dv-config header file, which is annotated for configuration wizard, we can configure our station, so our client. We can give him the SSID and the password that we are going to use in our Wi-Fi environment, the socket server IP that we use to communicate and for the test of the socket connections. And we can also enable or disable different tests. I know, for example, that in my Wi-Fi I don't have a DNS, so the get host by name test will definitely fail. And of course, there's no use in checking a failing test. So I just simply uncheck this box here so that this test is not run. Now I build the project, and then we'll take a look at the debug session. So I enter a debug session and start to run the program. I'm using System Analyzer, Debug Printf Viewer, and the RTX RTOS component viewer, and a small window where I am connected to the socket server so that I can check what is happening with the connections. In the Debug Printf Viewer, we see how the tests are executed and how they are passing. Sometimes we see some warnings, but that's nothing we have to worry about. And while we see that some of the tests are running, we see that the RxTX count are increasing on the socket server. And finally, we also do some speed tests. And the test basically then ends. Now let's take a look at the actual application, the Mqtt client and the software components. Of course, I use the same as before: board support, CMSIS RTOS2, KyleRTX, the CMSIS-Drivers. I need that for a functioning project. I still use the compiler event recorder and the standard out device components. Nothing has changed. What is new is that I use the IoT client, so the Mqtt client C software component, and I use in the IoT utility the Mqtt packet and the socket API I was talking about for Wi-Fi. And finally, I am using embed TLS for securing the connection to the server. I hit OK, and again we take a look at the main.c file, still system initialization, kernel initialize, and then we start in the main application. This main application again is nothing very special. We initialize the driver, set the power controls correctly, then we activate the driver and try to connect to the network. And if this happens, then we call the Mqtt client function, which is in the Mqtt pub.c file. Here we actually, for example, also connect to our Mqtt broker using some credentials. We check the unique user ID from the chip. So this is in the flash to be able to distinguish if we have, for example, multiple devices. And then we send basically the message to the broker Mqtt client with a certain message, basically the temperature. And for connecting the securely to the broker, we are of course using certificates, and this is in the certificates.header file. And I again compile this project as well, and then we go to debug to check what's happening. Build has finished. Now I flash download the program and enter debug. Flash download takes quite a while because it's only a CmSIS adapter, but it's on board, so it's easy to use. Here we are in debug. Before actually running the program, I check my server under this address here. I connect to it and I subscribe to basically all topics using the hash. I press subscribe, and now I will see all topics and messages in topics that are published here. I now start the debug session. We see the printf output that we are connecting to Wi-Fi. The connection succeeds, and then the message is published. And if I check my server, I can see that in this topic we have the payload of 26.36 degrees Celsius. So we can just compare the topic, for example, because I'm using the unique ID 7031. It's the same, so it's fine. If you want to learn more, here are some links that help you to get started. All CmSIS-Driver related documentation and software packs are available on GitHub. If you happen to be at the Embedded World trade show in Nuremberg at the end of February, visit us in Hall 4, stand 140, and learn more about how CmSIS and trusted firmware for Cortex-M help you to make your devices secure. More than 10 ARM employees speak at the Embedded World conference. Here's a small selection of our speakers. If you fancy a booth tour, don't forget to sign up in time. Thanks for watching this webinar. Hope to see you at Embedded World.